So, well, first of all, I would like to thank the organizers for this kind exinvitation and to talk about what I consider to be fantastic objects from many points of view. In fact, I'd like to think of binary neutron stars as Einstein's richest laboratory. And there were a number of things. There are a number of things I would like to talk to you about binary neutron stars, and some of these are listed here. But as you can see, we can look at the new binary neutron star to understand equations of state and doing gravitational wave spectroscopy. We can understand how magnetic fields play a role in the counterparts, how mass is ejected and leads to either a kilonova signal or nucleosynthesis, how you can understand what is the threshold mass to prompt collapse. All of these things are in principle interesting and related to binary neutron stars, but I will not be able to present them given the time I have. So I will concentrate on two topics, which are two lessons that I think we've learned from GW170817 on the maximum mass. And then about the possibility that we may use binary neutron star to explore a part of the phase diagrams that is not accessible in other terms. So let me start with the first point, first lesson, and this is about GW170817. So I don't think you need an introduction about this fantastic event. And let's see how you can use this event to understand a few things about the equation of state. So the most important of these aspects is, in my view, the limit on the maximum mass. And you may wonder, how is it that by just looking at the inspiral phase of a binary neutron star merger, we can deduce something on a completely different scenario, okay, which is the maximum mass of a non-rotating isolated star. You may think that the two are completely unrelated, but they are, in fact, related if you see them in the proper viewpoint. So what is it that we know is that GW170817 had a maximum total gravitational mass of about 2.7 solar masses, okay? That's really what we measured through the chip mass. Now, if you try and calculate equilibria models of self-gravitating objects in general relativity, you can fill a space which is marked by two parameters, the mass and the central density of the object you're building, the star that you're building. And to start with, you can look at non-rotating stars. These are spherically symmetric static objects. And when you do solve the couple hydrodynamic and Einstein's equation, which are also called the TOV equations, you obtain something like this in this diagram, a single line, which has a local maximum. And this is called the maximum mass of non-rotating stars. And that's because to the right of this maximum, you have unstable solutions. You can show that they are unstable, while to the left, they are stable. You can perturb them and they will not produce bad oscillations. Now, if you look at this diagram, it's a bit of a funny diagram because there are no numbers. And there is a reason why I don't show numbers. And that's because every equation of state will change the location of this curve. It will move it up and down, to the left, to the right, depending on the equation of state. And it is something that we are kind of used to. Now, this space actually has many more solutions than the one I'm showing you here. In particular, you can build in the green region the oldest solutions relative to uniformly rotating stars. So you can take a star starting, which is here, non-rotating, you can give some angular momentum, and you can fill a point in this space. And this green region is limited by another line, which is called the Keplerian limit. So all of the objects on this line are spinning at the Keplerian limit, and so that if you spin them a little bit more, it will break them apart. The star will start losing mass from its equator. And also this limit has a maximum, and we call this the maximum mass of rotating configuration, or M max. Now, what is interesting is that again, to the right of this Mmax, the configurations are unstable. You place a star here, you can build an equilibrium. There is no problem in building an equilibrium, but this is an unstable equilibrium. And this equilibrium will collapse to a black hole. And there is a smooth line joining Mmax and MTOV, and this is called a critical or stability line. Anything to the right of this line will produce a black hole, while everything to the left will be stable. Now, again, also in the case of Mmax, the position of Mmax will depend on the equation of state. So we don't really know Mmax and we don't really know MTOV, but there is something important that we know, and it is that we know that there is a universal relation between Mmax and MTOV. In other words, if we know one of the two, we know the other one. And that's because the maximum mass, Mmax, is 20% or so larger than MTOV. So whenever we know MTOV, we know Mmax, or vice versa. This is something that people had found, already in the 80s, in the 90s, but has been shown again more recently by myself and a student. And in particular, we've shown that not only there is a relation between these two masses, but there is a relation along all of the models on this line. And this is something new. Okay, I was saying that this is a very rich space of solutions. And in fact, there is another part which I haven't shown you, which is this one in this salmon color. These are all the differentially rotating stars. And as you can see, you can have stars which are differentially rotating with very low mass or very heavy objects over here. And of course, they can have much more angular momentums. That's why they are sitting outside of the green region. And again, you can show that the stability line is a smooth continuation of this line over here, and anything to the right of this line will produce a black hole, and anything to the left will not. Okay, so this is just a review of equilibria of relativistic stars. Now, how has this got to do with GW170817? What we know is that GW170817 must have produced a hypermassive neutron star, because the two component masses are way too large to produce any reasonable maximum mass. And so the object, soon after the merger, must have been here, must have been an equilibrium object, or quasi-stable equilibrium object in this position over here. Now, we also know that GW170817 produced a gamma ray burst. In fact, a very important gamma ray burst. And in the standard and most reasonable description of this process, this means that a black hole has been produced, because this has then launched a jet, and we've seen the gamma ray produced by the jet. Now, if a black hole has been produced, this means that GW17 has moved from here to somewhere in this region over here. And so you actually have two paths which are possible. The first path, which is like so, the object collapsed while it's still differentially rotating in the salmon region, or the object, took this route, became almost uniformly rotating, and then collapsed by crossing the line over here. And of course, these are the two possible options. But not all of them are equally probable, because in the path number 2, this takes place in about a few tens of milliseconds, and we know that GW170817 has produced a rather bright kilonova signal, and to produce a kilonova signal, you need to eject quite a lot of mass, and you don't have the time to eject so much mass if you go along route 2. So the evidence of a kilonova signal is hinting to the fact that it must have followed this portion, this track number 1. And now, effectively, you can also deduce that you can't have landed, you can't have crossed this line too far away from Mmax, because once you enter in this region, green region, you're essentially axisymmetric, and so you're not emitting gravitational waves, so you are not really prone to collapse. So if it has collapsed, it must have collapsed very close to this point over here. So this is the logic. Let's see what this brings us. We take the evolutionary track number 2, we measure the gravitational mass, we remove the rest mass that we can calculate from the kilonova. We, of course, need a conversion between rest mass and gravitational mass, but we know how to do this. And then we get this universal relation for the maximum mass. So MTOV has to be lower bound by this number. This comes from pulsar timing, and so it's an observational fact. But it's also upper limited by these numbers over here, 2.16. And if you take the genuine upper limit, you get 2.33. So this is a result that we have obtained in Frankfurt following this very logic. And if you're not convinced by this logic, that's fine, because around about the same time we came up with these results, 3 more groups using different logic, other simulations or kilonova, essentially got to the same result, 2.17, but roughly it's the same answer. So even if my logic is wrong, all the others' logics is right, the number still sticks. Okay, so now all of this was nice and satisfactory up until something happened. And you know, this is classical story in physics. You think you understand something, and then a new result brings you to a different conclusion. And this has happened with this guy over here, 1908-14. And this has created a tension on the maximum mass. And I'll explain why. So the binary as one object, the primary, which is obviously a black hole, 20 solar mass, it can be a neutron star. But the secondary, well, you know, it is either the smallest black hole ever seen or the heaviest neutron star. And so all of a sudden, if this object existed, then the maximum mass and all of I've been telling you is wrong, because you can easily produce an object with 2.5 or even 2.6 solar masses. Okay, so you know, we needed to see if there was a way to remove this tension or release this tension. Unfortunately, in the case of GW 1908-14, there was no counterpart. So, you know, it wasn't easy and possible to calculate ejected mass and do similar considerations. And so as a way to solve this tension, what we have done is the following. We have explored essentially how this assumption that the maximum mass can be even larger than 2.5 fits with all of our understanding that we have gained through GW 1708-17. And in practice, you know, from a mathematical point of view, all you have to do to study this problem is impose conservation laws of rest mass and of gravitational mass. And the observation tell you about the rest mass and the gravitational mass. In particular, gravitational waves tell you about this, kilonova tells you about this. And numerical relativity also allow you to fill in the gaps because we know how efficient the emission of gravitational waves is, and so how rapidly gravitational mass is burned during this process. Still, you know, this is a parameterized problem. There are many things that we don't know, and we express our ignorance through parameters. So effectively, in our model, there are 10 parameters. They need to be varied in order to, you know, find an answer, a distribution of answers, actually. So it's a multi-dimensional parametric problem. There are many different ways of doing this. Markov chain Monte Carlo is one. Something we instead like, because it's very easy and practical, is a genetic algorithm. So genetic algorithm is a beautiful approach, which is, you know, the same as in genetics. Essentially, you create a mutation, and which is just changing the parameters, and this mutation will be preserved or abandoned, whether or not provides you a better fit. In this case, not to the environment, but to the problem. And so, you know, we have implemented such a genetic algorithm for considering the hypothesis that, you know, the maximum mass is less than 2.3. If you remember, in 2018, the result we were giving was a flat posterior. You know, was just a uniform distribution. We didn't know much more, but we then recalculated everything on the basis of this genetic algorithm, and now we have a posterior distribution, which is shown here in blue. And as you can see, the two are in very good agreement. The maximum here is roughly here, 2.2, but the very maximum, the largest possible at 2 sigma is 2.32, which is roughly 2.33, which is what we were getting also from in the past. So all of this seems to match. But now we have a distribution function, and we can see how this distribution function allows us to check this prior with the other constraints. One of them is, how much gravitational waves can you radiate? And numerical relativity calculation tell you that, this is the range in gravitational mass that you can radiate. And I'm showing you here the distribution functions of the radiated mass once you assume the posterior that I've shown you before with the blue shaded area. This is the total gravitational mass radiated, which is the sum of the one radiated after the merger, which is the largest contribution, and the one during the inspiral. Inspiral is just a small contribution, as a matter of fact. Another constraint you can check is how much mass you are ejecting. And this is the range that you can constrain. This is a very small range, but important, and coming from the kilonova. And you can see again that the posterior distribution, assuming that the maximum mass is 2.3, fits perfectly with the expectation. Well, we knew this already in a way, but now we have a way of measuring this in terms of probabilities. Okay, then you can repeat the same thing now, assuming the second hypothesis, that is the maximum mass is larger than 2.5. And here you see the problem, the first problem, and that is if you concentrate here, I'm not using a distribution function. I'm just assuming that the maximum mass is as an upper limit of 2.4, this is the orange, or 2.5, and this is the red. And you can see that you overproduce by quite a lot the amount of gravitational waves. Again, dashed and dotted are in spiral and post-merger. So if you make this assumption, you are overproducing gravitational waves. And on the other hand, you are underproducing ejected mass. So 2.5 is in contrast, not only with the gravitational wave emission, but also with the ejected mass. And this is not too difficult to interpret. If you have a very massive object, this would be a very efficient emitter of gravitational waves, as you can see from here, and will collapse also very rapidly, and which means that it will not produce a lot of ejected mass. So going back to our question, how do we solve this tension? Well, there is just one way of solving it, and that is you have to admit that the secondary in GW at 1908-14 was a black hole at merger. But it could have been a neutron star early on in the evolution of the binary. There is nothing preventing this. But at the time we observed in gravitational waves, it was definitely a black hole, because otherwise it would be in contrast with all we know about gravitational wave emission and ejected mass. Okay, I have to hurry up now because I see I'm a bit late. Let me tell you about another aspect that is interesting. In Frankfurt, I work with colleagues who work in particle collisions, and they understand the universe in terms of this diagram, which is a phase diagram, where you have temperature and density and everything in the universe is placed in this diagram. And in particular, the early universe is over here, neutron stars are over here because they are cold and dense. Lattice QCD works here, collisions and experiments are over here, and you can see the neutron star mergers actually probe a region that is not seen by anything else, okay? Nuclear experiments are over here. So it is interesting to explore what happens when you have a merger, and in particular, if you can produce a quark phase. So that's what we've done. We have we have carried out simulations of neutron stars undergoing a phase transition after the merger. And for those of you who want to see this, this is obtained with a chiral mean field model, where you see that beyond a certain mass, you have a new branch, which is actually an unstable branch with a quark phase transition. Let me show you what happens in a situation like this. You have the two stars, which are hadronic, perfectly fully hadronic at first, then they merge as they normally do. Now, if I imagine, if you imagine to have a look at what is the quark fraction, you will see that this equational state will allow you to produce quarks in special regions of the star. In particular, these are the regions where the temperature and the density is very high. Now I'm showing you the temperature. So you have a 3 quantity measure of all the things that are going on. And at one point, the fraction of quarks will become so large, in particular at the center, that the equational state will soften. And if you remember, that's an unstable branch, and so the star collapses. Maybe it's easier to see them over here. You can see that there is a quark fraction. By the way, this is the quark fraction shown with this color code and temperature with this other color code. You see that where the temperature is high, there is a small, this is 10 to the minus 4, 10 to the minus 5 quarks. So it's teeny tiny amount of quarks. But then later on, at the center, the quark fraction becomes 1. At this point, the equational state softens and you produce a black hole very, very rapidly. You can see this in terms of gravitational waves. And this is shown here in black and red. Black is hadronic. The red is with a phase transition. You can see, so this is the evolution of the frequencies. This is the evolution of the phase difference between the two signals. Note that before the merger, there is no difference. That's because the stars are still hadronic during the spiral. But then after the merger, you start seeing quarks start appearing. This changes the structure of the star, even so slightly. And this then leads to a dephasing and a premature collapse of a black hole. Okay, so this is the smoking gun. You see the in spiral, you think, this is an hadronic equational state because I understand everything about this in spiral, but you would expect the collapse to happen here, and then instead happens earlier. You may ask, well, what happens if the two stars, you are very close to the maximum? Then everything would be, the difference would be very small. And indeed, the difference into collapse time would be very small and only a few milliseconds. But the ring down that you produce during the production of the black hole will be different. So again, you have another signature to, thank you, to know when it's a phase transition has occurred. So excited by this result, we have tried to consider a kind of classification, a zoological classification of all the possible scenarios. And this is shown in this cartoon over here. So imagine this is a spectrogram or the evolution of the gravitational wave frequency as a function of time. This is the time of merger. And this is the plain vanilla binary neutron star. It's hadronic and remains hadronic. And actually, we know these frequencies pretty well, and we know they follow universal relations. So we understand this NPT or no phase transition scenario. Another possibility is that you have a prompt phase transition. As soon as they merge, the conditions are such that you trigger a phase transition, and now you go from having a blue frequency to having a green frequency, which is different from what you would expect. And then again, a signature of a phase transition. You can have this other scenario, which is a phase transition triggered collapse. You see that you have at the beginning, there is no quarks, and quarks start to appear. And then these lead to the formation of, to the collapse of a black hole. And last, but certainly the most interesting in my view, is this one, the red one, which is a delayed phase transition. Essentially, you are still hadronic here, but then at one point, as temperature and density increase, you start producing quarks, but this doesn't lead you to a collapse. It actually leads you to a new equilibrium. And the new equilibrium clearly will be different than the previous frequency. And, this is a cartoon, but we've done this properly. And you can hopefully now see better. This is a no phase transition. You start here, you remain there. This is a phase transition triggered collapse. You first have a jump, and then you produce a black hole over here. This is again a no phase transition with a smaller mass. And here you have a delayed phase transition. You see that you first are in this frequency, and then you jump to a new frequencies over here. And this is important because you can see this in the spectrum, okay? This is the typical spectrum where you have a large F2 frequency in the hadronic case. And this is a case where you are hadronic at the beginning, but then you become quark later on, and a stable quark. And you can see this is very different from this guy over here. This is, here you have just one big peak, you have two peaks, and these give you information about the evidence of a phase transition. Okay, I want to stick to time. In essence, GW170817 has already provided a number of interesting limits, in particular on the maximum mass, but also on the radii, on the threshold mass, and so on. GW190814 has challenged these results, but I think this is a challenge that is easy to remove because having large masses is inconsistent with a number of things. And I've explained that a phase transition after a merger can give you signature of quark matter, and this opens a completely new way to explore quark matter in the universe. Okay, thank you.
Thank you very much, Luciano. So now there is time for some questions. Please raise your hands. Don't be shy. Okay, Anna Brennan.
Hello, thank you for the very nice talk. The quarks that you mentioned, the quark fraction, would these quarks be in isolation? And if so, would there be a possibility of having some kind of quark star as an intermediate stage between a neutron star and a black hole? Is that something that you would have maybe considered?
So in the first case, the equation set that we are considering allows you for a smooth transition between the two. So you have to imagine the quarks will start appearing and they will be mixed within the hadronic bath. You can also have a situation where there is a strong first order phase transition. And this is what we are thinking happens later on. Maybe I should go back here. When you are in this phase here, you can either have a hybrid star, a quark core and a hadronic mantle, or you may have even a purely quark star over here. This is a possibility that depends on the equation state. But from a phenomenological point of view, you will have the same kind of feature. Whether you have a hybrid star or a full quark star will change the value of the frequency here.
Okay, thank you very much.
Yeah.
Thank you.
Okay, Diego Blas.
Hi, can you hear me?
Yes.
Yeah. Hi. Yeah, very nice, interesting talk. Can you comment a bit more on the role of magnetic fields, or what is the status of simulating the magnetic fields in this very interesting?
Okay, so magnetic fields do not play any role in what I said because the maximum mass is not influenced by the magnetic fields. They can grow to be very large, but they cannot change. They are never comparable with the binding energy, which is at the end what plays a role in determining the maximum mass. However, if you allow me to have another half an hour, I could explain a lot about what we know about magnetic fields in binary neutron stars. In particular, we think that they can be behind the formation of a jet, which is natural and needed if you want to launch a gamma ray burst. So magnetic fields are actually very important. And there are some things which we understand, like the one I just mentioned, but there are many more things which we don't understand. And in particular, how strong can they get? Don't forget, you start with something which is pretty, as a moderate magnetic field, initially 10 to the 10, maybe 10 to the 11, not much more because these are very old stars. But then you expect to see something of the order 10 to the 15, maybe 10 to the 16, and how you go from one to the other is still very much unclear, and maybe will remain so.
And also the coherence.
And then the coherence, how you go from having a turbulent post-merger magnetic field to something which is, organized and coherent on a large scale. This is still, pretty much unsolved.
Okay, maybe a last question, Michaela.
Well, so first I want to thank you, Luciano, for your very nice talk. It's really very interesting. I actually do not have a question, but I have a comment, because there would be another possibility, say, to solve your tension between the estimate of the maximum TOV mass from the merger remnant and the much higher value, which you get from the other event. It's that in all your estimates, you assume the universality relation and also the maximum Kepler mass you obtain. You assume that the merger remnant is cold and in beta equilibrium. Because if you don't assume cold and beta equilibrium stars, then first universality of your relation between the Kepler mass and the TOV mass is broken. So you get an equation of state independence. And the second dependence you have is that you don't really know what is the entropy or temperature distribution and the electron fraction distribution in your merger remnant. So at the end, your estimate of your TOV mass gets a much larger error bar. And so
right. So this is a very good point, Michael. I should have been clear on this. And then let me just make sure that everybody understands what I mean. All of my considerations are made assuming that I'm referring to universal relation computed from cold stars, cold equations of state. But all of these curves over here will move. In particular, will go up and to the right if you allow for temperature dependence. Okay, if you say my star actually is not cold but has a certain temperature, and then you will have that these lines now become stripes, and you have to again follow the logic of these tracks, and this introduces new uncertainties. So this is, I think, a work that you have carried out, Michaela, recently, and in that case, if I remember correctly, you still find out that having a very large maximum mass is in contrast, so that you increase the uncertainty in the maximum mass, but 2.3 is still a reasonable value for the maximum mass. Do I remember this correctly?
Not necessarily.
Okay.
It depends really, because it's no longer universal. So this means that your result you get at the end depends a lot on the equation of state and on the Fermi effects on the equation of state, where we don't know much because all the constraints on the equation of state we have is essentially for cold matter. And the second point is we should know really for getting the stability line at finite temperature, you should know what is really the temperature distribution in the hot merger remnant when it collapses. And this is so you have the two additional uncertainties, and at the end, the estimate can go up to 2.5 or something like that.
Okay. Yeah. So I think the result is that because you increase the uncertainty on the location of this line and on the location of this curve, your error bars become larger. And so instead of having, something like this here, you have much larger error bars. I think you have two error bars according to, one on the temperature or entropy distribution, the other one on the whether or not you are near the stability line.
Okay, thank you. Perhaps we have to move on. Thank you, Luciano, for answering the questions.